NREL, and I'm going to talk about autonomous energy grids, and it's really our thoughts about reimagining optimization and control of future energy systems. So if we take a look at today's current power system, it's grown up over the last 120 years. It's really based on large central station generation, nuclear power plants, coal plants, natural gas plants, hydro plants, that are all at their heart based on a synchronous generator technology, so a big rotating machine that produces 60 hertz AC waveform here in the United States. And for the most part, it's centrally controlled, and in general, we dispatch this generation to follow the demand. If we look at future power systems, we see increasing levels of wind and solar. And these two technologies actually have some pretty different characteristics. First off, they're variable output dependent on weather conditions. And second is the fact that most of these are based on power electronics devices, which we call inverters, to connect to the grid. We're seeing increased use of communication, control, data, and information. Of course, when you start adding all these capabilities into the system, it adds a lot of efficiency and communication aspects, but it also introduces interoperability concerns as well as cybersecurity concerns. There's also a range of other new technologies like electric vehicles, distributed storage, flexible and controllable loads that we're seeing deployed on the grid. There's also increasingly interdependencies between the electric power system and, for example, the natural gas power system, so other infrastructures. At the end of the day, the future power grid is going to be much more highly distributed, much more complex than it is today to operate and control with all these different changes. So one of the things that we like to think about at NREL is looking out, 20, 30 years and seeing what's happening in the grid, for example. If you take a look at the current grid, it's very much this very hierarchical controlled system where you have big interconnects. In the Western United States, we have the Western Interconnect. Then you have regional transmission operators, people like CAISO, and then your local utility systems. PG&E, Southern California Edison, SDG&E, and then down, they also operate the local distribution system in a lot of cases, and you also have rural cooperatives and other municipal utilities at that level. So we know how to kind of run and operate this grid. We've been doing it now for basically a century, and even now where we have large interconnections with over 10,000 generators. In a lot of cases, they're running 5-minute markets, and they do 4-second power flows across the system. But again, if you look at the bulk generators, that's really only about 10,000 generators. Now, the question ends up being, how do you control a system that has got way more distributed devices? You could have hundreds of millions of distributed devices, whether they're PV systems, residential energy storage, electric vehicles that can control their charge, as well as smart appliances and smart homes. And we don't think the current central control mechanism is built to do that level of control. So one of the things that we spent the last couple of years looking at was developing what we call a distributed hierarchical control that would allow us to actually control 100 million distributed resources and large-scale generators and do 1-second optimization and not have issues with control times and things of that nature. And one way to do that, if you take a look at the figure here, is to take your grid and start breaking it up into smaller cells. Now, I'll just call them cells now. They could be microgrids where you could independently run a section of the grid in a standalone mode. But in this particular case, we don't necessarily have to have that islanding function. We could just operate and manage the grid at a cellular level like this. So we started to think about this on how you would actually deploy it and how it would work. We did an example project where we were able to study and look at an example. For example, if you took the Bay Area of the grid, so around the San Francisco Bay, that is a power system at the distribution level that has more than 10 million electrical nodes. And if you think about 4 million, over 4 million customers in this space, if everybody ended up getting PV on their roof, energy storage, smart homes, plug-in electric vehicles, you're talking about 10 to 20 million controllable devices. And right now, we don't have the infrastructure or the distribution system management systems that even could do anything close to this. So we started to think about how could we actually deploy distributed controls in this type of scenario. When we started looking at it for the power grid, we also quickly realized that you have other infrastructures or areas that have similar challenges when you start to do them at scale. So the transportation sector, if you have autonomous controllable vehicles and electric vehicles, if you have buildings, large-scale deployment of renewables, all of these sort of have these common underlying theoretical problems associated with it. And we've tried to develop basically a way of handling all of this together, because you really have to focus on how do you address several different challenges like real-time optimization and control, hundreds of millions of control points, asynchronous data between all of these systems, and very complex systems. So the way I'm going to describe this to you is kind of lay out a challenge here where we had to come up. If you take a look at the little diagram here, this black line represents a distribution feeder, and maybe these little green dots are all your distributed resources. So we needed something that was very fast. If we're operating and doing real-time optimization and control, say on a second-by-second level, what we needed to do is break these complex systems up into small size chunks, we call these cells, and then optimize interior to each cell. So that's what these little diagrams here represent, is the optimization of each of these cells. And then we needed it to be scalable, so that not only were we just doing this at the distribution level, but you could use the same techniques whether you went down to a home or community level, or if you went up to the bulk power transmission system. So that scalability and using the same algorithms was key to making this work. And the other thing was, how do you take and make best use of data that's embedded in here? So there's lots of data points, lots of measurements being made, but none of it is all nicely time synchronized. How do you bring that information in and make best judgments while you're operating a real-time system? So I'll give you an example of kind of how this thought process worked. We'll take a look at the whole grid here, as you can see, and lots of pieces of that. So, for example, wind farms, buildings, vehicles, the grid itself, and making into small microgrids and the like. But what I'm going to do is I'm going to take a quick example of this wind plant, because it's the easiest thing to grasp the concept, and then we'll apply it over to grids. So this particular diagram right here, each of these little arrows represent a wind turbine pointing into the direction of the wind blowing in a wind farm. And that's usually made, that the decision is made on the back of each wind turbine with the anemometer back there. This is a typical wind farm on the left, and you can see over here on the right how nicely time synchronized all of that was. We'll just run through it again real quick. But again, each of these little arrows is a wind turbine. It's making a measurement of wind direction. And in this case, for example, some of the wind turbines are interfering with each other. But if you look at the right-hand side, you'll notice that everything seems to be extremely synchronized together, and things are moving much more smoothly to determine the direction of the wind. We did this using a distributed control algorithm. So the way it works is we basically take that wind farm, we break it into cells, and then inside each cell, we have the wind turbines communicate with each other and come to consensus on which way the wind's blowing, so they can all face in that direction, and then they pass that information on to the neighboring cells. And each of these cells are also internally communicating and passing that information back and forth, so that very quickly the entire system can come to consensus on which way the wind is blowing. In doing this, that we've been able to show that actually we can reduce the solution times for coming up with this optimal power direction decision, reduce it from about 14 minutes down to 2 seconds, which allows for about 2% more energy on an annual basis. And so we've been working with wind farm developers on how to deploy this technology in their wind farms. But this kind of gives you an idea of when I start talking about the grids, the cellular approach, how we actually make decisions about how the grid of the future will be controlled and operated. So now let's take a look here at the grid itself. So similarly, again, we take a distribution system in this case. You can see a substation here and then several parts of the grid, and we're able to segregate those into different areas. And by doing this, what we're able to do is drastically increase the reduce the amount of time it takes to come to optimal solutions. And the optimal solutions could be voltage levels or power flows or a variety of things. We then actually can break it into smaller levels. If you take a look here at this one, we were making smaller and smaller breaks in the system. Now these, again, they could be microgrids where they could operate independently, but we left these all as grid connected, but we're looking at how to do the optimization and control of a fully grid connected system like this. And at the end of the day, we saw drastic, 30% improvements of how fast you can come to optimal solutions while maintaining the accuracy of these designs. So what we're able to do basically is in our second and third year of this project, we basically looked at how we could take really complex distribution circuits with many, many distributed resources deployed across here. So we were looking at 12,000 just on this one single circuit. But then we did a step further and started to build entire complex grids like the Bay Area up together. So we pulled it all together. We basically took the entire Bay Area power grid, broke it into small operating cells, and then we're able to show that these things would work together. So I'll show you how that works here in some little diagrams. So remember, as an example, this is San Francisco right here. So this is just one region in the San Francisco Bay Area. And inside of that, when you look at these diagrams, you'll see we've deployed PV generation, buildings, and electric vehicles and charging stations. So, of course, what you're seeing here is a simulation. This is not the real world of what's happening right now, but we have the simulation running at a scale that goes all the way down to individual PVs on individual buildings and individual cars charging and running around the city. So this is a little bit nicer figure here where we deployed around 300,000 PV systems. So each of these little yellow dots is a PV system deployed in the Bay Area. And then on about 400,000 buildings in the Bay Area. And then we added in about 10,000 electric vehicles and 200 charging stations. And when we run this over time, this is a little quick sped up simulation here where you can see some clouds passing over, and that's going to impact the PV output and the like. But what we're able to do basically is simulate the entire Bay Area, 10,000 electrical nodes, 1 million deployed resources, and show that these advanced control algorithms could actually work with time steps of 1 second. So every second, things are changing on here, and you can see all these little dots are changing color and things like that. But the important part here is that eventually we could build advanced control algorithms that could be deployed with the utility that are distributed in nature, yet come to the proper solutions across these larger integrated grids. So as you can imagine, we've taken this sort of idea, and this is kind of another little video that shows an example if we're trying to maintain proper voltage. Typically, voltage levels, when you have lots of changing resources, don't change that often, and you may not be getting the optimal voltage profile. But if we could break the system into these smaller cells, have the cells communicate with each other, you potentially could get this more optimal voltage profile on distribution circuits that would allow for more renewables or better power flows across those systems. Now, I showed you a lot of simulation work. We've also started to demonstrate this in more actual equipment. So in our laboratory at NREL, we set up a experiment where we had 100 actual devices. So it could be battery energy storage systems. You see some of those located in this picture here. It could be electric vehicles. It could be PV inverters. And what we did was actually deploy these algorithms actually into the controllers for these devices, and then connected them through what we call hardware in the loop. So we take a simulation of a distribution circuit that you can see here and connect the outputs of these technologies into the simulation so that as the simulation changes, it affects the grid conditions that the devices would see. And we conducted a experiment where we had 100 different actual operating devices in a single experiment that showed how these distributed controls would work. And now we're actually deploying in the field. So we're working with Holy Cross Energy in Aspen, Colorado, which is a rural co-op in the Aspen area. And you can see they're putting in new smart homes with solar PV on the roof. They also have battery energy storage systems, electric vehicle chargers, other smart home controls. And we've been able to deploy these same controls and show that they work in a real world setting. There's more information on this if you're interested in some of these links. So with that, I'll wrap up this particular part of the discussion, which talked about autonomous energy grids, and maybe we can take some questions here now before I switch over and talk about the grid forming inverter pieces. Here, I'm going to talk next. Let me do this just to save some bandwidth, and then I'm going to put this presentation up. Okay. So my next presentation, it gets away from this high-level control, but it still talks about how these systems all work together. And what I'm going to talk to you about today is a new consortium that actually will kick off here in January. We've been working on the development of it for about a year. But I'm really going to talk about the need for grid-forming inverters in the future power system and why this, I think, is the most critical topic to address to achieve 100% clean energy goals. As most people, hopefully on the phone here, know that most inverters that are connected to the grid right now are what we call grid-following inverters. They look for a reference waveform, a 60 hertz signal from the grid. They synchronize to that, and then they inject power. But what we're going to talk about today is grid-forming inverters and why that's a necessity. Okay, so I'll speed through these first couple of slides, but realize that 2020 was a seminal year. We had some really amazing things happen. If you take a look at the U.S. energy supply at a big, high level, one of the amazing things that's happened is that for the first time, who knows, in quite a while, if ever, that as long as the power grid itself has been around, is that renewable energy, including hydro, wind, and solar, actually produce more energy than either coal or nuclear. So some amazing feat there where renewables are really starting to get deployed at a massive amount. So in general, for the last 10 years, we've seen this big decline in coal usage, increasing use of natural gas and renewables, and nuclear and hydro have pretty much remained steady. The other big thing that happened last year was the fact that of this 20% annually from renewable sources is across the continental United States, is that wind produced more than hydropower. So for the first time ever, hydropower remained pretty constant here, but wind actually produced more energy across 2020, and solar is rapidly getting deployed. So, you know, what's causing that? At the end of the day, economics drives practically every decision, and the cost competitiveness of wind and solar has finally reached a point where they are the lowest form costs of new electricity. So if I had to go out and put in a plant today, these are average costs for the United States, and of course the wind and solar are going to depend on your wind and solar resources, but in general, they are significantly lower on a cost per megawatt hour basis for a new plant. Now, the big challenge here is that wind and solar are not dispatchable resources. They're variable resources, whereas these other technologies, you can turn them on and off and are dispatchable. You know, what's really driving this at the end of the day, we see a variety of things. The costs are probably the number one thing, but also states and also utilities are setting clean energy targets in the U.S. So the blue states here highlight states with clean energy mandates, but the interesting thing is the green areas. Those are utilities that may stretch over multiple states that also have things like 100% decarbonization goals. So that's why you see things like here in the Carolinas, this is Duke Energy service territory. And the Biden administration set these very aggressive targets. I think everybody in California is very aware of this kind of stuff. But 100% clean electricity by 2035, that's only 15 years away. I guess 14 years away now. So this is a very aggressive goal. And I always like to do this little thought experiment, which is, okay, 100% clean electricity. If we keep the nuclear fleet, it's around 20% of our energy. Hydro, we're not really building a lot of new hydro. That's about 7%. And maybe we replace a lot of the natural gas with some kind of clean burning hydrogen fuel system. Even if you add all this together, you quickly come to the realization that we probably are going to need the entire United States to be running on 50 to 70% annual energy basis from wind and solar. Right now, we're at 10%. So we got to go to 10 to 50 and above in 14 years. That is a massive change in the electric power system. So what do we know about running grids with high levels of renewables? If we take a look at sort of power systems that are actually up, installed, and operating, if you look at this graph, you see system size running along the x-axis, all the way from a tiny 100 kilowatts up through, we got a megawatt, then 10 megawatts, 100 megawatts, a gigawatt here is right in the middle, and out to 1,000 gigawatts. 1,000 gigawatts is the installed generating capacity of the continental United States. And then percent wind and solar here on the y-axis, two numbers to be aware of. And hopefully you can, I don't know if you can see my pointer or not, so I will turn on the little laser pointer. Right, this square, red square is instantaneous level, and what that means is at any particular point in time, it's going to be at that amount of wind or solar. But that could be 5 minutes, could be an hour. Doesn't have to be that long. And then the annual energy is over the entire year. So we know on small island power systems how to run these grids with very high levels of wind and solar. This little picture here in the middle is Tau Island in American Samoa. It runs a 100% solar system. Now, it has a very big battery, and it's got a very large solar system for the size load. This is a 150 kilowatt nominal load, and it has over a megawatt of PV, so about 10 times the load size in deployed solar, and then it also has a large battery on it. The other thing with these other island systems like King Island in Australia, El Hierro in the Canary Islands, they also have large amounts of energy storage. So you can see here this wind-focused system has got a pumped hydro plant associated with it. But in general, we can run these systems at 100% inverter-based grids. Now, the key thing here is that these are all very centrally controlled. We have one place where all the inverters are co-located together. They are not distributed around the island at all, and we can set up all the protection for these systems in a very small location. So but we know how to do it. If we go to slightly larger systems, now we start to move into systems that look much more like the grid that you would know. So we start off in Hawaii with Kauai and Maui. These systems have generation distributed all over the island. They have some large plants. This is a large wind plant on Maui, but they also have distributed photovoltaics on people's roofs. They have many plants everywhere. They have a transmission and sort of a transmission and distribution system, but if you think about it, they have many voltage levels across the island, and they also have a small control center for the island. And then things like Crete in Greece and the country of Ireland, as well as Northern Ireland, these are operated as a single power grid. And they range in sizes from roughly a little under 100 kilowatts up to 6 gigawatts in size. And you can see here, in general, we know how to run fairly high levels of instantaneous power, although Ireland, as we get bigger and bigger, this number is actually being limited, and this number is being limited by the system operator. In the Hawaiian Islands, we're letting those go higher, let's just say. And actually, some new news on these numbers, actually just this year in 2021, Maui was operating at basically around 90% instantaneous values, and Ireland let themselves go up to 70% instantaneous. But the challenges really revolve around how do we get these instantaneous numbers up here toward 100 so that these average numbers can get above 50. And then as we look at larger interconnections, two examples here, ERCOT, the Texas Power Grid, and the Western Interconnect of the United States. Actually, ERCOT earlier this year was able to run at 66% instantaneous wind and solar. So these are creeping up, but at the end of the day, you can see here everything together. What we need to do is find solutions to the technical challenges to get these levels here much higher. So we really need to look at how the power systems operate at all times during the entire year and make sure that we come up with solutions for getting to 100% inverter-based instantaneous levels. And then you can imagine during the year it's going to fluctuate with the amount of synchronous generators that you have online. So a little bit of the technical challenges with integrating machines and inverter technologies. So this is the big power grid, but it could be a microgrid. But in general, when we interconnect the Western Interconnect of the United States, we are electrically tying synchronous generators that are in hydro plants, nuclear, coal, natural gas, all together through the electric power grid to create basically a large virtual machine. And what that means is that if, for example, you have a problem where one of your generators drops out, this generator will pick up that load automatically. Now, it won't pick it up instantaneously, but the inertia that's happening inside these machines allows the system to continually run. When we connect devices like induction machines or inverters, they don't have the same tight physical electromechanical coupling that synchronous generators do. But we're working on developing advanced controls for PV inverters, wind turbine inverters, battery inverters that actually mimic that response characteristic and are able to keep the system in synchronism even as we experience faults and the like. The key here is that we need to basically unify the operation of synchronous machines and inverter-based resources at any scale. So it could operate at 100% inverters, could operate at 100% synchronous machine, or anywhere in between. So here's some of the technical challenges. I'll just list them kind of quickly and talk about them. But one of the things that you need to maintain is voltage and frequency stability, right? So if we go back to this diagram here and we drop off one of these generators, that's what happens typically when you experience a big fault on the grid. So it's humming along at 60 hertz, you lose a generator and the frequency declines very rapidly until the rest of the generators can pick this system up. So this blue line represents how long it would take to recover that system in terms of, this is time in seconds. And then the red line here actually represents if we were to program the inverters that are online at a specific time, how it could improve that capability of bringing the system back to nominal frequency. This is typically what we call an inertial response. And for the inverters, we use the term fast frequency response for this characteristic, where we're able to detect this high change of frequency and have the inverter start to pull back the grid. Now, historically, I would say before IEEE 2018 came out, the inverters would see this drop, and if it went below the tripping frequency, the inverters would just trip offline. But what we're looking at now is we get higher and higher levels of inverters. We'd like them to stay online and participate in actively keeping the stability of the grid in place. So that's one of the challenges. Another one is protection. It sounds like at your last meeting you had people from SEL come in and talk about protection. I won't go through it in too much detail, only to say that protection of the grid is an important aspect. And what we mean by that is the ability to recognize that a fault has occurred and then to isolate that fault and then keep the remainder of the system operating properly until that fault is cleared. But here's the big challenge in a nutshell with inverter-based resources versus synchronous generators. Typically when a fault occurs, say here at time 0, a synchronous generator will put out something around 6 times rated fault current. It's a big spike in fault current. It's easily seen if you are watching the waveform. And so devices can see this and react to it, whether it's a relay, a breaker, a fuse, whatever protection equipment you're using. But for inverter-based resources, they typically don't have the capability to do that high level of output. You can see here a couple examples. Inverter number 1, this red line, it sees that fault happening and actually disconnects as quickly as possible, and then the fault current goes to 0. Or you can have the inverter program to recognize that fault current. It actually is going to produce a little bit more, maybe 1.1 times its rated current, and then it'll ride through here for 7 cycles, and then it'll disconnect. But in either of these cases, they don't look like the blue line, and our protection systems historically, especially overcurrent protection, has been designed to recognize the blue line condition, and it would have a very difficult time discerning these type of outputs when you have low fault contributions from the inverters. So again, just another thing to be aware of. In addition to that, when you think about if we move to a system that was 100% inverter based, you also have to design the fact that these systems have to be able to recover from an outage condition. So some of your inverters need to have some grid forming capability to restart the grid, and that we typically call that a black start. We've been investigating that on how you use inverter-based resources to black start systems, but there are challenges with that. For example, when you black start a grid, you have to re-energize transmission lines and transformers, and so you need to make sure that your devices would have that capability to actually re-energize those pieces of equipment. The entire process of restarting the grid is called system restoration, and building all these devices and having them adequately planned to work together to restart the larger grid is an important part of thinking of how to operate a system with that much inverters. And then finally, there's a couple other things just to be aware of, things like control system interactions and system resonances. So depending on how these inverters are actually doing their control algorithms, potentially they could be causing technical interactions with each other that might cause problems on the grid. We really have little understanding in this space because we haven't deployed that many grid forming inverters all running simultaneously. And then another big concern is cybersecurity with this many distributed resources, mostly all having some communication aspects with them. I'll just point out that, again, these systems are not impossible to build. This is an example. We actually had our substation at one of our campus facilities go out on us, where we lost the utility for several weeks. But we actually were able to, since we have lots of assets around, we quickly took a large wind turbine, PV system, and battery bank, configured it in such a way to actually run and operate our building loads and we were actually able to show that we could run this for 72 hours without any grid, 100% inverter-based microgrid, if you will. Although this wasn't reconnecting back into the grid itself, it did operate as an independent microgrid for 72 hours. So this kind of showing you here, the gray is the load, pretty constant load, then the solar coming up, then going down at night, then the wind turbine coming on, and then this is the battery charging. But we were able to demonstrate some advanced controls, including black start for these types of systems. But again, this is only relatively small, under 2 megawatt size system. So that's where Unify comes in. So this is a consortium that was designed, as I mentioned before, we're getting ready to kick it off here in January. We've been kind of prepping behind the scenes over the last couple of months to get this rolling. This is funded by the Department of Energy Solar Energy Technology Office initially, along with industry cost share, to bring the industry together to kind of solve these challenges of how you get more grid forming capability into these inverters to make them operate across the grid. And again, the vision here is that we will be able to seamlessly integrate any mix of machines and inverter-based resources at any scale. As I mentioned before and kind of showed that graph, right? What we're trying to do here is address these challenges that I kind of talked about on the earlier slides and get this line up here so that at instantaneous levels, we could be running close to 100% inverter-based at any physical scale. So we have ideas on how to do the research, how to demonstrate these concepts at scales, how to develop best practices and standards for this, and train the next generation workforce for this future grid. This isn't something brand new to the industry. We had to do this 100 years ago. You can see this picture here is from 1904. A joint meeting of what became the IEEE, where people were starting to parallel a lot of synchronous machines together, and they had to figure out the rules of the road to get the synchronous machines together. But a lot of those ideas we could then apply back to inverter-based resources, and really we're providing this platform to engage all of these people together to make this a reality. You can see here a list of the project team members. Just, highlight, we have 4 national labs, 12 universities, including universities in California. EPRI is a co-lead on this, and then a set of inverter manufacturers, the real-time system simulation software vendors, and a set of utilities, including Southern California Edison and PG&E, as well as other people that are involved on this. You can see kind of the areas that we're doing work on. So in the R&D area, trying to work on modeling and simulation for these grid forming controls, the controls themselves, the hardware, how you integrate these and validate their performance. And then we have larger scale demonstrations, how you take this information and move it towards the standards development organizations, and how you educate people on all of this work. There's some additional industry partners that we have in here, including California ISO, who's a close partner on understanding how to deploy these systems. I'll just skim through this quickly in terms of what we're trying to do. I'll focus right here on this interoperability guidelines and functional requirements. So let me go to the next slide. So what we want to do is develop sort of a set of rules of the road from a system level of ensuring stable system operations, maintaining voltage and frequency, black start capabilities when you look at these types of grids. How do you pass secondary control signals, so a higher level control for optimization? And then individually at the inverter level, so the individual inverter technology, how does it do its own autonomous primary control? What type of signal is needed to talk to the utility itself? And how do you ensure power quality and protection requirements are followed? I'll highlight, we do a seminar series on Mondays at 1 to 2 p.m. Pacific time. I think we just finished the fall 2021 earlier this week. You can see the number of speakers we had. And then we're starting up a spring series here in January that'll be running through the spring, where we get together as a larger group and talk about grid forming technologies, the latest and greatest operations, and things along those lines. And with that, I'll end this presentation and take questions from you. So thank you.